A fully furnished 10-story apartment complex materializes from the ground up in 28 hours and 45 minutes. This is not a temporary structural shell. The modular assembly includes pre-installed walls, complete plumbing networks, active electrical wiring, and fully finished balconies. The same engineering team subsequently erected a 57-story skyscraper in Changsha, China, completing the entire structure in 19 days. Following that metric, a 26-story residential tower emerged in just over 5 days. A conventional construction project of that specific height requires an average of 16 months to reach basic completion. The schedule collapsed. The raw data reveals a severe operational discrepancy between standard practices and this new methodology. The individual responsible for this acceleration holds no degree in architecture. He possesses no structural engineering background whatsoever. Before initiating these rapid assembly protocols, he operated a business selling commercial air conditioning units. How does a climate control vendor permanently alter the critical path of high-rise construction? The transition from manufacturing cooling equipment to redefining global building methods originates from a specific physical failure. The events of the year 2008 forced a complete investigation into the physical limits of traditional concrete. On May 12, 2008, this air conditioning executive witnessed the catastrophic physical failure of standard concrete. A magnitude 8.0 earthquake tore through Sichuan province. The ground released massive kinetic energy across a vast fault line. Standard construction materials met this lateral force with sheer static mass. It was a fatal physical mismatch. Traditional concrete weighs approximately 2,400 kilograms per cubic meter. It is exceptionally heavy. It is inherently rigid. When the earth heaves violently, this dense material cannot flex or absorb the kinetic shock. The seismic waves travel directly up the rigid structure. The structural columns snap under the pressure of their own immense weight. The air fills with the sharp, explosive crack of fracturing support pillars. This sound is immediately followed by the deep, resonant rumble of thousands of tons of material collapsing downward. Nearly 70,000 people died in the aftermath. Schools, residential blocks, and hospitals folded into mountains of fragmented rubble within a matter of seconds. Zhang Yue, the founder of the manufacturing company Broad Group, closely studied these ruins. He realized the disaster was not simply a result of poor maintenance or outdated building codes. The fundamental physical properties of heavy concrete were the actual mechanical threat. The global construction industry relied entirely on a rigid, brittle material that shatters instantly instead of yielding to stress. The core problem was the sheer weight and inherent inflexibility of standard building materials. Understanding the physical vulnerability of heavy concrete, Zhang Yue shifted his established air conditioning factory lines to an entirely new task. He dismantled the traditional logic of the construction site. Unpredictable wet processes were eliminated in favor of exact manufacturing tolerances. The entire supply chain, previously optimized for thermal regulation units, was abruptly redirected toward the mass production of residential modules. Instead of hiring conventional architects, Broad Group recruited specialists from the aerospace sector and industrial manufacturing. Housing was no longer treated as a bespoke local project. It became a standardized mechanical product requiring precise metallurgical specifications. Aerospace engineers applied their methodology to steel frames, calculating load distribution with the same parameters used for aircraft fuselages. This industrial shift required years of testing. Early iterations yielded multiple failed prototypes, forcing the engineering team to repeatedly redesign structural joints and rethink the assembly sequence. They systematically removed variables like weather delays and material curing times from the structural equation. Tolerances were zero. Every component had to meet exact factory measurements. Finally, after extensive validation, the initial technical drawings transitioned into tangible steel modules moving along the indoor assembly lines. Industrializing the architectural process demanded an enormous indoor footprint. The manufacturer established a covered production hall spanning 230,000 square meters. This immense facility rivals a major automotive assembly plant in sheer volume. Inside this controlled environment, building design turns into pure mechanical engineering. Every single section becomes a standardized unit. Its external dimensions precisely match a 12-meter shipping container. The core construction finishes months before any heavy machinery reaches the vacant property lot. Inside the facility, technicians route copper wire through precision-cut steel channels. Plumbers seal internal water pipes. Ventilation ducts slide into their designated overhead mounts. No raw materials sit exposed to the harsh weather elements. Then the module collapses. Exterior walls fold completely flat against the floor grid. Heavy steel balconies hinge inward. The glass windows remain fully fitted within their frames during this entire procedure. This mechanical compaction allows standard highway trucks to transport the bulky units without requiring specialized wide-load logistics. The physical assembly requires zero field welding. Once a flatbed trailer reaches the destination, heavy cranes hoist the compressed sections into the air. The folded walls swing outward. Sharp metallic clicks echo across the lot as workers drive high-tension steel bolts to lock the multi-ton modules together. Each new structural connection fastens directly to the adjacent unit. The site sees zero liquid materials. The complete elimination of poured concrete removes all scheduled delays tied to material curing times or sudden rainstorms. Because every module arrives fully finished, the location loses its traditional status as a construction site. It becomes a pure assembly zone. This shift redefines the logistics chain. In a conventional project, dozens of subcontractors deliver raw materials to an exposed area. They fight weather, coordinate overlapping schedules, and build everything from scratch. Here, the process mirrors a production line. The modules undergo rigorous quality control inside a climate-controlled facility before transport. The tolerances are tight. Measurements are verified to the exact millimeter using industrial alignment systems. The contrast is stark. Correcting a structural error on a traditional site means demolishing cured concrete or tearing down erected steel frames in the rain. Fixing a flaw in a dry factory involves adjusting a mechanical component before the module even reaches the loading dock. Workers on the ground do not fabricate or alter anything. They simply lock pre-inspected units into position. Human error drops. By the time flatbed trucks deliver the folded modules to the zero-cycle foundation pad, every dimension is guaranteed to fit. To validate these strict manufacturing tolerances, engineering teams deployed cameras across an active foundation site in Changsha. This major industrial hub in Hunan province hosted a severe logistical trial. 3 heavy cranes initiated an uninterrupted mechanical sequence, transferring folded components straight from transport vehicles onto the mounting points. The continuous installation rhythm persisted through daylight and nighttime conditions, demanding strict pacing from the deployment crews. From the initial lift to the final bolt secured on the 10th floor, the sequence consumed exactly 28 hours and 45 minutes. The resulting time-lapse documentation immediately forced rival firms to evaluate this disruptive methodology. Proponents recognized a genuine structural paradigm shift. Vocal skeptics dismissed the operation as a choreographed demonstration thoroughly isolated from standard environmental variables. Instead of publishing technical rebuttals, the corporation answered this deep skepticism by preparing blueprints for a significantly larger tower. The revised blueprints materialized in Changsha as Mini Sky City. 19 days, 57 floors, a height of 204 meters matches the 58-story Trump Tower in New York City. The entire assembly process operated without a single structural pour of wet concrete on the active site. Logistics dictated a continuous rhythm. Heavy transport trucks deliver modules in a tight sequence directly from the manufacturing plant. Cranes hoist the prefabricated sections continuously into the air. The heavy machinery hums across the site day and night. Operators position the steel-framed modules, which already contain factory-installed electrical wiring, plumbing pipes, and ventilation ducts. Installation crews lock the mechanical joints using high-strength bolts and immediately signal the crane operator for the next lift. Over 90% of the entire building mass arrives at the foundation completely finished. A standard reinforced concrete skyscraper of this exact vertical scale demands at least 24 months of continuous labor. This modular tower required under 3 weeks from the first floor slab to the final roof section. One specific logistical elimination made this rapid timeline possible: 15,000. That is the exact number of wet concrete truck deliveries erased from the construction schedule. If parked bumper to bumper, those heavy vehicles would form a line stretching over 100 kilometers. Without the mandatory curing periods for concrete columns and floor slabs, the vertical climb accelerated to 3 full floors every single day. 1,200 workers focused strictly on bolting the geometric sections together rather than building formwork, tying rebar, and pouring structural elements. This streamlined supply chain directly cuts on-site silica dust and significantly lowers local noise pollution for the surrounding district. By removing unpredictable construction variables, the builder controlled every minute of the mechanical assembly. Developers who previously ignored prefabricated architecture reviewed the certified Changsha timeline. City planners and institutional investors began demanding similar modular schedules for future commercial zones. After the 19-day assembly of Mini Sky City, engineers compressed the timeline even further on their next urban project. The Jingdu Tower reached 26 stories. A standard concrete high-rise of this exact vertical scale typically requires a permanent crew of several hundred people working continuously for 12 to 14 months. How did just 100 on-site workers erect 26 floors in exactly 5 days? The construction velocity relied entirely on installing fully finished structural modules delivered straight from the manufacturing floor. There were no unpredictable weather delays, no contractor armies waiting for traditional wet concrete to cure, just a synchronized operation involving heavy cranes lifting prefabricated steel units into place. But this accelerated structural pace immediately triggered severe safety concerns. When a residential building rises faster than a standard week of office work, the psychological barrier replaces the logistical one. The public inherently questioned the structural integrity of rapid assembly. Consequently, major institutional investors diverted their scrutiny from construction schedules, shifting their focus to demanding rigorous physical safety inspections and stability tests. The growing anxiety over structural stability required definitive technical proof. The China Academy of Building Research provided exactly that through comprehensive dynamic load tests. Their engineers subjected the rapid assembly components to extreme kinetic pressures. The results defied standard architectural expectations. Broad Group utilizes engineered steel modules. They are 10 times lighter than conventional concrete panels. Simultaneously, these metallic units prove 100 times stronger under intense directional stress. Most modern concrete high-rises have a firmly calculated lifespan. Engineers design them to last 50 to 100 years. Standard poured concrete resists seismic force through rigid mass. When tectonic stress exceeds the material tolerance, the foundation snaps. Microscopic fissures rapidly propagate through the load-bearing walls. Once concrete starts fracturing under pressure, the mechanical failure becomes entirely irreversible. The structural integrity permanently collapses. Steel handles massive physical loads through a completely different principle. A prefabricated steel framework actively absorbs kinetic energy. It does not fight the incoming force. During a severe seismic event, the bolted nodes physically deform. A distinct metallic creak echoes through the interior shafts. High-tension bolts take the raw structural weight. The steel frame flexes several degrees off its vertical axis. After the primary kinetic wave passes, the metal components recover. They return to their original geometrical position without permanent damage. The Academy certified these modular structures to withstand extreme forces. They can survive a magnitude 9 earthquake. This sudden energy release represents a massive seismic event. It is the exact equivalent of the devastating 2011 Tohoku tremor in Japan. Standard concrete inevitably shatters under these extreme conditions. Bolted steel modules dissipate the shock waves across thousands of flexible connections. This physical flexibility changes the architectural timeline. It grants the rapid assembly towers an estimated operational lifespan of 1,000 years. The modular design eliminates the destructive life cycle of urban infrastructure. Workers connect the structural grid utilizing high-strength steel bolts. They do not use poured chemical mortar. The high-rise never becomes permanent monolithic waste. If local zoning requires spatial changes, teams can systematically unbolt the entire tower. Every individual steel module can be physically extracted. It can be transported and reassembled at a completely different site. Alternatively, crews send the components directly to a smelting furnace for complete melting and recycling. Beyond resolving seismic vulnerability through fully recyclable components, these bolted steel structures eliminate the massive volume of unrecoverable debris. Traditional construction methods generate millions of tons of unrecyclable reinforced concrete every single year. Workers routinely discard disposable timber formwork, excess mortar, and unusable rebar offcuts directly into overflowing dumpsters. A standard commercial site produces mountains of crushed stone and hardened sludge that end up occupying municipal landfills for decades. The Broad Group, operating out of Changsha, replaces this chaotic disposal cycle with a highly controlled factory environment. By shifting structural production indoors, their modular assembly process reduces overall construction waste by 90%. The footprint remains remarkably clean. There are no concrete crumbs scattered across the ground, and no tangled piles of rusted iron bars waiting for removal. This specific approach removes the primary problem of modern building sites by discarding the need for single-use molds and wet cement mixtures entirely. While crews in Changsha focused on stacking prefabricated steel frames, a different engineering solution began taking shape simultaneously. Another technology firm based in Shanghai initiated a competing method to eliminate material waste using an automated heavy construction portal. The engineers at the Shanghai-based company Winsun scaled up the exact mechanics of desktop fabrication to industrial proportions. Instead of bolting steel components together, they deploy a massive extrusion portal the size of a commercial logistics warehouse. The primary gantry spans 32 meters in length and 10 meters in width. A heavy nozzle moves precisely along steel guide rails. It extrudes continuous ribbons of a dense, highly viscous compound. The mixture of pulverized construction rubble and fast-setting cement leaves a distinct wet shine as it stacks layer upon layer. This steady mechanical layering eliminates the requirement for temporary wooden formwork. Wall by wall, the internal and external structures rise simultaneously. This extrusion method alters the fundamental economics of structural architecture. Traditional concrete construction charges a severe financial premium for complex geometric shapes. Curved forms require expensive custom molds and intensive manual labor. An automated printhead does not differentiate between a standard straight line and an elaborate curve. The nozzle simply follows the program's spatial coordinates. A curved wall costs exactly the same as a standard flat barrier. The machine removes the financial penalty for complex architectural design. The operational efficiency metrics show a sharp contrast with standard building practices. Overall material consumption drops between 30 and 60% compared to conventional concrete pouring methods. There is zero loose structural waste left on the ground. The construction timeline shrinks drastically. During one continuous production cycle, the Winsun portal fabricated 10 complete houses in exactly 24 hours. Each individual structure cures and hardens within days. The entire physical operation requires only a fraction of a standard manual site crew. The heavy portal equipment executes the physical process strictly according to the loaded digital blueprint. The elimination of massive on-site manual labor suddenly pushed these extrusion technologies far beyond the established limits of Chinese megacities. Across vast regions of Southeast Asia and Africa, growing populations face a severe and immediate deficit of affordable shelter. Traditional fired brick manufacturing requires immense thermal energy, and complex truck transportation over unpaved regional roads drives basic material prices far beyond local purchasing power. Supply chains break down. Automated digital printing bypasses these deeply entrenched logistical bottlenecks completely. Heavy field equipment effectively replaces scarce skilled manual labor directly on the actual dirt of the construction site. When a seismic event or severe flood strikes an isolated territory, transportable portal systems offer a rapid response. The heavy extruders configure structural emergency relief shelters within just a few hours of deployment. Remote rural communities now receive functional medical hospitals and solid primary schools without the prohibitive financial penalties of standard material haulage. In many developing nations, the population grows much faster than conventional contractors can mix and pour standard wet concrete. One engineering approach stacks heavy prefabricated modules. Another extrudes specialized cement mixtures directly on the ground. Both methods bypass the fundamental vulnerability of traditional open-air manual assembly. Precision replaces guesswork. The global automated construction market expands consistently as traditional contractors fail to recruit enough field workers to meet worldwide infrastructure demands. Traditional construction hits a hard physical limit of available hands just as the global housing deficit crosses a critical threshold. The world currently lacks 100 million residential units. The demographics outline a strict operational ceiling. In the United States, the average age of a field construction worker exceeds 40 years. The manual labor pool shrinks annually. Veteran framing crews and concrete masons retire from the daily physical strain. Young apprentices do not enter the trades fast enough to replace them. A standard residential site requires dozens of manual specialists working simultaneously in unpredictable weather. When those specialists vanish, project schedules collapse and costs multiply. A global deficit of 100 million homes collides with state injections exceeding $1 trillion. This volume of capital demands a delivery speed that manual bricklaying can no longer physically provide. The global modular construction market reached $95 billion in 2025. Industry analysts project a steady climb past $175 $1.5 billion by 2034. The Asia-Pacific region currently controls roughly 45% of this entire manufacturing sector. China alone allocated over $1 trillion to infrastructure and urban development in its current national planning cycle. Transitioning to controlled factory assembly is dictated strictly by these rigid demographics and hard economics. Governments across the globe recognize this impending demographic trap. The United Kingdom commits billions to off-site fabrication programs. Japan and South Korea scale factory-built modular structures across both residential and commercial sectors. However, the most definitive proof of this shift happens in Southeast Asia. A dense island nation of 5.9 million people relies heavily on the State Housing and Development Board for affordable high-rise shelters. The city-state no longer treats automation and factory modules as a mere alternative for urban expansion. Singapore legally mandated volumetric modular construction methods for all new public housing projects. Despite state-backed investments pushing modular solutions, the technology routinely stops dead in front of century-old building regulations. Regulators across most major economies meticulously wrote their local codes for poured concrete and traditional timber framing. They do not include clear legal provisions for factory-assembled volumetric steel modules. The International Building Code, which forms the baseline for many jurisdictions, only issues comprehensive updates every 3 years. Integrating a radically new assembly method requires prolonged physical testing, political lobbying, and bureaucratic consultation. This administrative inertia extends deeply into established construction supply chains. Heavy equipment rental companies, specialized material suppliers, and regional subcontractors operate on long-term contracts structured around site-poured concrete. They possess zero financial incentive to dismantle their existing revenue streams. Labor organizations also actively resist the transition because modular construction fundamentally requires fewer active personnel on a live building site. Less physical site work means significantly fewer billable hours for the skilled trades relying on conventional building timelines. A controlled factory environment can manufacture and ship a fully finished apartment block in a matter of weeks. Yet municipal planning departments remain calibrated to the slow pace of standard construction. The speed of physical assembly directly collides with the reality of slow administrative paperwork. Consequently, regulatory bodies freeze these high-speed modular projects indefinitely at the initial permit issuing stage. Physical proof of this bureaucratic blockade emerged quickly. Developers abruptly canceled the tallest planned modular structure on Earth. Engineers designed the Sky City project in Changsha to reach 838 meters. Why did they abandon this record-breaking skyscraper? The local financial and regulatory environment simply rejected the blueprint. Site preparation stopped immediately. Instead of hearing loud cement mixers pouring a massive foundation, managers faced silent stacks of rejection letters. The engineering mechanics worked flawlessly. The legal framework failed entirely. This sharp contrast defines the modern global housing crisis. In China, assembly crews construct a 26-story tower in just 5 days. Cranes lift prefabricated steel units into precise vertical slots continuously. Meanwhile, Western real estate markets remain trapped by traditional administrative delays. A standard mid-rise residential building in New York requires extensive municipal processing. Inspectors review every minor architectural change. From filing the first zoning permit to handing over the keys, London developers wait 3 full years. While traditional zoning stalls conventional building projects for 36 months, sheer economic pressure accelerates a different physical reality. Decreasing material waste and shrinking delivery timelines drive this shift. The victory of the factory method becomes a matter of time. Material properties dictate the final outcome. Conventional reinforced concrete remains highly porous. It absorbs atmospheric moisture over decades. Internal steel rebar corrodes, expands, and cracks the surrounding cement. This chemical process limits standard commercial structural lifespans to roughly 50 to 100 years. The factory alternative completely abandons wet pouring. It relies entirely on dry assembly and dense composite alloys. Instead of pouring liquid cement into wooden molds on site, technicians bolt together pre-finished structural panels. They maintain millimeter tolerance. This dry assembly approach allowed one manufacturing crew to erect a complete 10-story residential block in under 24 hours. Elsewhere, a massive robotic gantry processed crushed industrial rubble. It fed the aggregate through a high-pressure extrusion nozzle. The machine printed 10 separate houses within a single day. These composite mixtures resist water ingress far better than standard concrete. A modular structure, fully manufactured on an assembly line and bolted together in 28 hours, holds an official engineering certification. It is rated for 1,000 years of continuous use.